So, dear colleagues, we're all here, therefore we can start. Yes, okay. So, good morning, dear colleagues and guests. It's July 29th, 2021, 2 p.m. noon, Moscow time. And we're beginning the panel session for the defense of the thesis by Abouzalam, Alaa, Mohamed, Ahmed. The thesis is submitted for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 139 according to the new nomenclature, plasma physics. Previously, this specialization was coded as 010408, plasma physics. The essence, they don't change, but the code has changed. And the topic of the thesis is panning ionization processes in rydberg cold medium. So we open our panel session. Under the order issued by the Academic Secretary of St. Petersburg State University, Alexander Gnyotov, as of May 13th, 2021, and according to it, I, Nikolai Timofeyev, Doctor of Sciences in Physics and Mathematics, Professor, Head of the Department of Optics of St. Petersburg State University, was appointed the chairperson of this dissertation board. The order also approved the candidacies of all the members of the board, and let me introduce them. Vladimir Sakhamlinov, he is here with me, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Optics of St. Petersburg State University. So he is here in our hall, and the following members of the board are working in the remote mode. Valery Smirnov, Doctor of Sciences in Physics and Mathematics, Associate Professor of the Department of Optics of St. Petersburg State University. Valery, do you hear us and see us? Yes, I do. Okay, Maxim Golubkov, Doctor of Sciences in Physics and Mathematics, leading researcher at the Laboratory of Chemical Physics of Nanostructures of the Semyonov Federal Research Center for Chemical Physics of the Russian Academy of Sciences. Maxim, do you hear us and see us? Yes, I do. Igor Ryabtsev, Doctor of Sciences in Physics and Mathematics, corresponding member of the Russian Academy of Sciences, Head of Laboratory of the Zhanov Institute of Semiconductor Physics, Siberian branch of the Russian Academy of Sciences. Igor, do you hear us and see us? Yes. And Marcis Auzenš, Doctor of Sciences in Physics and Mathematics, the University of Latvia. Do you hear me and see me? Yes, everything is okay, thank you. Okay. And we also have our candidate for the degree, Abouzalam, Alaa, Mohamed, Ahmed. And we also have the thesis supervisor, Nikolai Bezuglov, Doctor of Sciences in Physics and Mathematics, Professor of the Department of General Physics 1 of St. Petersburg State University. I would like to inform you that the panel session of the dissertation board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted into English and into Russian. And here I would like to make two comments. The first comment is as follows. If anyone wants, and by the way, that's addressed to those who are working in the remote mode, if anyone wants to go for a certain period of time to leave our session, you should warn me about that, and I will announce a technical break. And if the person will be absent for some time, this person loses the right to vote. Unfortunately, these are the rules and provisions of defense at our university. That's the first point. And the second point, the defense will be held in English. Alaa will make a report in English, but we're going to have simultaneous interpretation from Russian into English and vice versa. And in order to simplify the work of the interpreter and the board, I ask you to speak Russian, because otherwise we need to change channels all the time, and this takes certain time and may lead to certain difficulties. So Alaa will speak English and we are all going to speak Russian. No objections about that. Okay, so these are the technical remarks that I wanted to make. Currently, we have an email address posted on the page with live broadcast of the board session. And all listeners can submit their questions to Ms. Abouzalam Alaa online, the questions regarding the thesis or scientific discussion. These questions will be forwarded to me by our technical service, and I will read them out during the discussion. The questions should be related to the presentation and the content of the thesis, and do not forget to give your name and position if you submit a question. The questions that have nothing to do with the scientific discussion or dissertation text or assessment will not be voiced. Now a few words about the specialization that I believe we need to make, because the code of specialization was changed and all the documents were prepared according to the previous code. Abouzalam Alaa Mohamed Ahmed had submitted an application for the defense according to the specialization 010408 plasma physics. However, in order to meet the order of the Ministry of Science and Higher Education of the Russian Federation as of February 24th this year, on the approval of nomenclature of scientific specializations, according to which we have the right to defend doctoral and candidate thesis, and by the way, this order was approved as of November 10, 2017. So we have a new nomenclature in place for specialization, and taking into account the fact that our dissertation board was previously approved by the order of the academic secretary of St. Petersburg State University. So it was approved according to specialization 010408 plasma physics. And it was approved, by the way, for the defense of Mrs. Abouzalam Alaa. It was formed according to the topic and according to all the requirements. So regardless of the fact that the code of specialization was changed, still nothing has changed essentially. And according to the provision on the defense of academic degrees at our university, a specialized council is gathered for every defense, so we choose experts that work with the appropriate topic. And in fact, regardless of the fact that the code has changed, that's a formal change, and essentially nothing has changed. And the title is the same, plasma physics, and we have just the code that was changed, so taking into account the application of the candidate for the degree on the change of the code of scientific specialization. So the old nomenclature is 010408 and the new nomenclature is 139. So the changes were introduced into the order on the approval of the academic board, and we changed the code here. Therefore, we are going to listen to the report that meets the requirements of the new specialization as well. So, dear colleagues, are there any questions or remarks on this issue? No questions as far as I'm concerned. Everything is clear. Okay. So, the defense of the thesis for the thesis titled Penning Ionization Processes in Rydberg Cold Media is held according to the scientific specialization 139 plasma physics. That's it. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local normative acts, the session of the dissertation board is valid, providing 2/3 of the appointed board members are present. And the total number is not to be fewer than 4 people. The dissertation board consists of 6 people. Everyone is with us today, including 4 members of the board that are working remotely. We have a multimedia connection with all the members of the board, as well as with our candidate for the degree. Therefore, we have a quorum, and we can hold our session. And our session should not last more than 2 hours. And the agenda is as follows. First of all, we're going to listen to the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements. and chairman's replies to questions, if any, and I'm already doing it. Then we're going to listen to the candidate's presentation, providing an overview and findings of the research. 15 minutes for that. Then questions to the candidate regarding the presentation, no more than 2 minutes per question. The candidate's replies to questions. Follow then the reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions. They will state their positions and make offers. 10 minutes per speaker. Then the chairman's report on the thesis. I also have 10 minutes for that. Then the candidate's comments about the reports on the thesis and replies to the questions. Then open discussion. Anyone present at the defense may state their position or ask questions on the thesis, or maybe submit specific offers on the topic of the research. And I kindly ask you to fill in the registration form and introduce yourself before I give you the floor. Then the chairman will ask the questions submitted during the broadcast via our website. Then the candidate's replies to the questions. Then the presentation of the candidate's thesis supervisor. 3 minutes for that. And I ask the thesis supervisor to characterize not the work, but the work of the candidate for the degree. Then we're going to have a 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. The discussion of the results of the defense is not broadcast. Then we're going to have open balloting, vote counting and recording of the results in the protocol. And then we're going to make a decision on whether to confer the academic degree or not. And finally, we're going to listen to the candidate's closing speech. So, distinguished colleagues, any questions or comments on this agenda? If there are no questions, let us proceed. But before we do that, I kindly ask you to switch off the sound on your mobile phones. Thank you. Well then, the chairman's presentation. A thesis by Abouzalam, Alaa, Mohamed, Ahmed for the academic degree of the candidate of sciences in physics and mathematics, the specialization 139, plasma physics, is titled Penning Ionization Processes in Rydberg Cold Media. A thesis was approved for the defense by the order of the academic secretary of St. Petersburg State University, issued April 8. Abouzalam Alaa Mohamed Ahmed has prepared her dissertation at St. Petersburg State University, and Nikolai Bezoglov, Doctor of Science in Physics and Mathematics, Professor of the Department of General Physics 1 of St. Petersburg State University, is the thesis supervisor. 3 published works describe the research findings. They include no papers published in the peer-reviewed journals recommended by the Ministry of Education and Science, and 3 papers in Publications Index and Web of Science and Scopus. The candidate has submitted the full set of documents to the academic secretary, and the above-mentioned documents comply with item 12 of section 3 of the order on the procedure of granting academic degrees at St. Petersburg State University. And all the documents, as far as I'm informed, comply with the requirements and are found in the certification file. And curator of the defense, member of the Department of Dissertation Board Support, has all the copies. She's present here with us. That's Natalia Karpova. And before I give the floor to our candidate for the degree, I would like to ask the members of the board if there are any general questions to the candidate for the degree, and is there a need to consider the whole list of documents submitted by the candidate for the degree. So no questions about that. Okay. So let's shift to the report. Then, the short report of our candidate for the degree. Alaa, I would like to remind you that you have 15 minutes. And the report will be delivered in English. So, Alaa, please, you have the floor.
Good afternoon, Chairman, members of the Dissertation Council, and my colleagues. This work presented by me, Alaa Mohamed Ahmed Abouzalam, under supervision Professor Beziglov Nikolai Nikolovich. The title of our thesis is Benign Ionization Process in Cold Media. In our presentation, we talk about, firstly, the aim of our work and the expected results, define rydberg atoms and their characteristics, followed by describe how rydberg atoms can evolve, application of rydberg atoms and how it evolves into cold plasma. Secondly,
I beg your pardon, can we give the presentation on the screen because we don't see the presentation? So it was sent previously. So I should, yes, I should turn it on my screen. Okay.
Сейчас, одну минутку, подождите.
Yes, because we need to turn on the presentations ourselves. Okay, is it? So, colleagues, do you see the presentation today, right now? So, does everyone see the presentation? No, we don't see it. Those who are working remotely, they don't see the presentation. Yes, you need to switch the screen in the upper part. In this case, you are able to see the screen. Igor, you should turn on the presentation. You see the screen. Okay, thank you. Alaa, you can continue.
Then we describe the binary model of benign ionization, followed by describing the numerical technique used to calculate benign auto-ionization widths and our semi-classical approach. Finally, we display the results of our work and the conclusion of our work. The aim of our work is to study benign ionization process caused by long-range dipole-dipole interactions between highly excited alkali rydberg atoms in a cold media. Procedures was done within the framework of Simarnov-Katsura model and the semi-classical approximations. We have investigated the features of benign auto-ionization widths as a function of the principal and orbital quantum numbers of the colliding atoms. The expected results with the existence of optimal atomic pairs, we obtained analytical formulas together with the tabulated values of the two parameters included in them, which make it possible to calculate benign auto-ionization width for the main orbital configurations for all alkali metal atoms. As we mentioned, we concerned with alkali rydberg atoms. Rydberg atoms are atoms at their highly excited states with exaggerated properties compared with the low excited classical atoms. This table demonstrates for us some properties of rydberg atoms. The most important in our work is the radiative lifetime and the dipole moments. Actually, the attractivity of rydberg state systems is related to the existence of huge electric dipole moments. From this equation, we can calculate the energy level for the alkali atoms. The main ionization process in the system of cold rydberg atoms is photoionization by exciting laser, photoionization by black body radiation, and benign ionization, which is the aim of our work to study the physics of benign ionization and to calculate benign ionization rates. Rydberg cold systems have a wide range of applications. Have a wide range of applications. For example, in astrophysics, in strongly interacting systems, and in plasma. In strongly interacting systems, as we mentioned, rydberg atoms have a huge electric dipole moment, and as a result, if we have two close rydberg atoms, there is a strong interaction between them, and as a result, we can control this interaction by what's called the dipole blockade. In plasma, at sufficiently high principal quantum numbers, Rydberg atoms can spontaneously interact with a large number of other atoms, and they tend to spontaneously to ionize to form cold plasma. In this slide, we demonstrate how Rydberg atoms can evolve into cold plasma. For example, in cold gas of rubidium atoms, initially excited into identical states with principal quantum number equal 0 and principal quantum number equal 50 and orbital quantum number equal 0. A spontaneous transition of Rydberg medium into a cold plasma is observed over a range over a period of about 100 nanoseconds. This transition occurs via the so-called diffusion stage of the cold gas evolution. This evolution is accompanied by redistribution of excitation energy between Rydberg states, resulting in the formation of asymmetric atomic pairs with a broad range of quantum numbers. Long-range dipole-dipole interactions between two Rydberg atoms can result in production of a free electron due to resonant Auger-like process. The energy level diagram illustrates the Benign ionization process between two interacting Rydberg atoms. They interact via dipole-dipole interaction. We have two atoms. The atom is undergoing a downward transition, and as a result of this downward transition, there is a released energy absorbed by the other atom, I atom, and as a result, they transferred to the continuum.
Виктор, что там у вас?
The condition for this interaction to take place, the released energy from downward, resulting from the downward transition, should be greater than the binding energy of the I atom. For this condition to take place, the downward transition should be below the threshold limit, which is represented by the blue line. This interaction can be represented by this formula, which represents the Benign ionization process between two Rydberg atoms, resulting in production of free electron. The rate of formation of free electron is determined by auto-ionization rates of quasi-molecule consisting from two interacting atoms. The rate of formation, of transition from the initial state to the final state is expressed in terms of dipole matrix element of bound transition and bound free transition. Our method to calculate Benign ionization rate constants is based on Simarnov-Katsura model, which requires the electronic shells of the atoms don't overlap. Rydberg atoms are randomly located in space and have a homogeneous distribution over Zeeman sublevels of the excited states. We can calculate the Benign ionization rate from this formula. The reduced Benign auto-ionization width includes reduced dipole matrix element and photoionization cross-section. To calculate the reduced dipole matrix element and photoionization cross-section, we need to calculate what's called the radial integrals, as we can see from these formulas. To evaluate the radial integrals, we use the semi-classical formulas from this work expressed via modified area function. The accuracy of our representation assumed to be 3% for radial integral and 5.5% for photoionization cross-section in case of bound free transition. We can see this from this figure, which demonstrates the results of photoionization cross-section as a function of the principal quantum number. The dashed line represent results calculated via our semi-classical representation, while the solid line represent the results obtained from quantum mechanical calculations obtained from this work. Results and discussions. In this section, we discuss the features of Benign ionization process inherent in alkali metal atoms with focus on identifying the difference from hydrogen atom. We calculated the Benign autoionization width for all alkali metal atoms as a function of the principal quantum numbers of the two colliding atoms. And here we present an example in the case of lithium atom with the two different orbital configurations, SS and SB. The third figure for the hydrogen atom with orbital configuration SS. The first important feature we can observe from this figure is the oscillatory structure in the values of Benign autoionization widths upon variation the values of the principal quantum numbers, and this is related to the dependence of the nonlinear dependence of Rydberg energy on the principal quantum numbers of the colliding atoms. The second feature we can observe also common between hydrogen atom and the alkali metal atoms is the general growth in the value of the reduced Benign autoionization width with the simultaneous increase in the value of the principal quantum numbers of the colliding atoms. And this feature doesn't surprising us because as the atomic size increase, the dipole interaction between them increase. The last feature we can draw from this figure, the hydrogen atom characterized by an insignificant dependence of the value of Benign autoionization widths on the orbital configurations of the colliding atoms. In the contrary, all alkali atoms display a strong dependence on the orbital configuration. This feature appears clear more in this figure, at which we consider different atomic species and orbital configuration. For example, the lithium atom display a strong dependence on the orbital configuration. For example, the values of Benign autoionization width for the lithium atom with SB orbital configuration increased by 3000 then from SS orbital configuration. From this figure, we can observe a strange behavior of the Benign autoionization widths, which is the values of the Benign autoionization widths increased associated with the decreasing of the principal quantum number of the de-exciting atom at fixing value of the principal quantum number of the ionized atom. This feature surprising us because classically when the atomic size decreases, the interaction should decrease. But this feature is related to quantum mechanical feature of photoionization cross-section and radial integrals as a function of their arguments. This feature is not restricted for alkali atoms, but also the hydrogen atom display the same behavior. From the values of ND optimal can be calculated from this formula, and this table illustrates the values of ND optimal for hydrogen atom and alkali metal atoms. For more illustration, how the value of Benign autoionization width increase when the symmetric pair is replaced by an optimal pair, more clear in this slide, at which we consider the Benign autoionization width for symmetric and optimal pairs as a function of the principal quantum number of the ionized atom. For example, when Ni equal 100, the Benign ionization efficiency increased by 1000 when the symmetric pair is replaced by an optimal pair. From this slide also we can demonstrate the accuracy of our calculations. The curved line represent our analytical results, while the zigzag line represent our numerical results. Besides our numerical results, we succeed in obtaining analytical results. At Rydberg states, our semi-classical approximation allow us to obtain significant simplification for radial integrals and photoionization cross-section, which make it possible to obtain formulas for Benign autoionization with averaged over oscillation as a function of the two parameters, scale parameter pi and shape parameter xi. We calculated the values of the two parameters for all alkali metal atoms and for hydrogen atom, and here we present an example in the case of the potassium atom compared with the hydrogen atom. It's precious to mention that the values of the two parameters turn out to be independent on the orbital configuration in the case of hydrogen atom. In this slide, we provide a comparison between Benign ionization rates calculated according to our approach and the black body radiation induced photoionization rate. We use this accurate and simple formula to calculate black body radiation rates adapted from this work. For this aim, we consider an example called the system of rydberg atoms, initially with symmetric pairs with principal quantum number equal 31 and orbital quantum number equal 1, may evolve into the diffusion stage into the optimal pair with principal quantum number ND equal 17 and Ni equal 89 for the SF orbital configuration. The corresponding Benign ionization rate is found to be 25,400 second minus 1, while the black body radiation rate is found to be 470 second minus 1. Such a rate turns out to be 45 times smaller than Benign ionization rate. All of this confirmed that the main role played by Benign ionization process. In this figure, we demonstrate the rate of different ionization channels and at the diffusion stage of Rydberg gas evolution into cold plasma. Conclusion. Based on Smirnov-Katsura model, the present work analysis Benign ionization process caused by long-range dipole-dipole interaction between highly excited alkali Rydberg atoms in cold media. Within the framework of semi-classical approximation, we have investigated the features of Benign autoionization with dependent on the principal and orbital quantum numbers of the quasi-molecule formed by atomic pairs of Rydberg atoms. We have found and described the optimal, highly asymmetrical configuration of Rydberg pairs of all alkali metal atoms, leading to a strong intensification of the free electron arising due to the Benign ionization process, as distinct from the case of hydrogen atom. The difference in quantum defect of atomic series for alkali metal atoms leads to a strong dependence of the Benign autoionization widths on the orbital quantum number of the atomic pair. The work provides analytical formulas together with the tabulated values of the two parameters included in them, which make it possible to calculate Benign autoionization width for the main orbital configurations for all alkali metal atoms. The initial excitation of the selected Rydberg states can be accompanied by rapid population redistribution over a wide range of Rydberg states with an explosive increase in the Benign ionization rates up to 5 orders of magnitude as a result of the formation of optimal pairs. All the above properties of Benign ionization make it a relevant source for producing seed charged particles in cold Rydberg systems that spontaneously evolve into cold plasma. Here we demonstrate our publications and reference. Thank you.
Спасибо, Alaa.
Thank you, Alaa. And distinguished colleagues, please, questions, if there are any. Are there any questions to the work? May I ask a question? Yes, please. I have the following question. We understand it. So Alaa came to the empty place, and that is the full direction. And I see that she did a lot. She has made a huge step forward, and I like the work very much. So I have a question to Alaa. I see that you worked in a team. So what result do you see as your best result from the point of view of what you did? What difficulties did you face, and how did you manage to overcome them?
Please, I can't hear the question. If you please, you can.
Максим Геннадьевич, еще раз повторите, пожалуйста.
Maxim, could you repeat the question once again? Okay, the question is as follows. What result of your work do you see as the main result of the work? And the second question, what difficulties did you face, and how did you manage to overcome them? So that's the main question that I wanted to ask.
As I understand, the main results of our work is to obtain semi-classical formula to calculate Benign auto-ionization width.
Okay, I got it, and thank you. Thank you.
Удовлетворены?
Are you satisfied with the answer? Yes, I read the dissertation carefully, so I understand what the candidate for the degree is talking about. Okay, thank you. Other questions, please? Alaa, I have a question to you as well. Could you please tell me, right now you've considered in your work the alkaline metals, and it's clear that alkali atoms have weak bound electrons. Therefore, the formation of rydberg atoms is something that is done quite easily, if we can say so. So we can presume that they are formed easily. Could you, for example, use your model and your calculation to in more complicated systems? For example, alkaline rare earth metals like zinc, for example, cadmium, or quicksilver. Maybe this will lead to huge computational difficulties.
According to our results, we obtain simplification for calculations for atoms. For example, for zinc, as I understand, for zinc.
Щелочно-земельные металлы.
Yes, alkaline rare earth metals.
The simplicity or what? The simplicity for calculation.
Спасибо.
Вы имеете в виду наши подсчеты для щелочноземельных металлов?
Спасибо, спасибо. Еще вопросы, пожалуйста.
Okay, other questions. So I have another question that is present in my review, but still, I would like to repeat it. Maybe there's some new information in place. Alaa, could you please tell me, the topic of work as I see it is quite interesting and quite fascinating. Are there any experimental confirmation of your results?
No, there is no experimental confirmation. Our work is hard to experimental work until now.
Спасибо. Пожалуйста, еще вопросы.
Thank you so much. Other questions? No questions. Okay, thank you then. Natalia, do we have any external reviews submitted or any external questions? No. Okay. Now we switch to the speeches of our board members. First of all, I would like to remind you that the reviews were submitted before the changes of the code. Therefore, I have the following questions Question: dear members of the board, do you agree with the fact that we recognize these reviews as the reviews that comply with the new scientific specialization 1.3.9 point plasma physics? Do you agree with that? That your reviews can be considered as the reviews for this novel specialization? So you agree with that? Okay, thank you. As all the reviews were already published on the St. Petersburg State University website, I offered to give just the basic points and basic questions to our candidate for the degree. Do you support this idea? Okay. Okay, now let's read our reviews. And my review will be the last one. First of all, I would like to give the floor to Professor Smirnov. Please, Professor, you have the floor. Well, I won't read it out completely. I would like to say that the work is quite relevant, it's quite interesting and useful. And I have 3 remarks that do not compromise the overall high value of the work, and I believe Alaa deserves the degree. So these are the specific remarks that I wanted to read out. First, in table 1.1, in the 2 penultimate lines, you have an unfortunate title used, the energy of an electron in a field, and you'd better use energy of an atomic dipole in the field. Then, second remark. In chapter 4, we have the results of calculating the effect of pi amplification, and they refer to the density of rydberg atoms in 10 and taken to the degree of 12. And these states are considered up to n that is roughly 100. And for such states, the indicated density is close to the maximum. And the contribution of not only 2 particle but also 3 particle interactions becomes large. To exclude the rule of 3 particle interactions, the density of rydberg atoms should be reduced by an amount of 2 orders of the magnitude. And a third remark. This formula 6.3 for the radial integral corresponds to the Hermitian nature of the dipole interaction. The matrix element must change to the complex conjugate element when the initial and final states are interchanged. And obviously the definition of the radial integral satisfies this condition, but the expression 6.3 does not. It must be an even function of the difference between quantum defects, and otherwise asymmetry occurs when moving up and down along the levels. And the same question is for formula 6.4. So that's it, what I wanted to say. Okay, Alaa, you can answer the questions and the comments.
Thank you, Professor, for your feedback about the first remark. Thanks for your comment. We agree with your opinion. Sorry for this misunderstanding. For the second remark, yes, of course, I agree with your opinion, Professor. Actually, this is not our results. This figure represents illustration adapted from this work. Our aim is to demonstrate the efficiency of Benign ionization caused by dipole-dipole interaction. So we consider the binary collisions for this densities and the principal quantum numbers. The electronic shells don't overlap. For this reason, our model more or less okay. Interaction with other atoms will increase the Benign ionization rate, so we can relate our results to the minimum limit of the Benign ionization rates. The third remark, our semi-classical formulas for radial integrals imply a special configuration for the levels involved. The final state must lie above the initial state. If we deal with an inverse configuration in order to preserve the self-adjoint property, it's necessary to change the sign of the quantum defect. Formulas 6.3 and 6.4 describe radial integrals in the case of transition down and up respectively, and match to the above results different sign of the quantum defect, which guarantee the self-adjoint. Thank you.
Валерий Владимирович, вы удовлетворены?
Valeria, are you satisfied with the answers? Yes? Thank you so much. So in the third case, you introduced this formula artificially. So it's clear, yes. Thank you. The answer is clear, so I'm satisfied with the answers. Okay. Thank you, Valerie. Next, I would like to give the floor to Professor Sakhamlinov. Please, you have the floor. So, please take a seat and turn on the microphone. We can't hear you. Yes, as the previous member of the board, I would like to read out just remarks and the general conclusion. I have 4 remarks. So first of all, I would like to mention that the work is quite relevant, and it is prepared at a very high scientific level. Therefore, I have no doubts that Alaa deserves the degree of the candidate of sciences. And the remarks are as follows. Some specific properties of radial integrals and photoionization cross-sections as functions of the arrangements are indicated on page 166 of the thesis as the reasons for the appearance of optimal Rydberg pairs, and the specificity itself turns out to be hidden, and the whole series of parameters of quantum configurations on pairs included in the formulas on page 160. And as a wish, I would like to have a visualization in the form of graphs of the behavior of radial integrals and photoionization cross-sections. Second remark. There is a contradiction between the graph in figure 6.2 on page 203, the criterion for the appearance of the first resonance presented in the form of formula 1.5 on page 139, and the discussion on page 184 of the fact that the auto-ionization width grow 5-fold in the vicinity of the resonance in comparison with the hydrogen atom. However, according to formula 1.5, it is the configuration of the levels of the hydrogen atoms that corresponds to the resonance criterion. Third remark. Figure 3.4, shown on page 165 to illustrate the Tom and Jerry effect, is emotionally interesting, but as an illustration of the effect itself, it adds nothing new. And the final remark. When describing the semi-classical formulas A7A9 and Appendix A on page 223, the important role of quantum factor lambda q is emphasized in improving the accuracy of semi-classical calculations. It is not clear from the text of the dissertation how this factor was obtained. But as I've already mentioned, these remarks don't compromise the overall high value of the work. The candidate for the degree, Alaa Abouzalam, deserves the degree of the candidate of sciences and physics and mathematics. Thank you, Vladimir. Alaa, you can answer.
Thank you, Professor, for your feedback about the first remark. We agree with you. For this reason, we present these figures from previous work, adapted from the previous work. Frame A demonstrates the values of photoionization cross-section as a function of photoelectron energy, and as we can see, the photoionization cross-section increase when the the cross-section decrease when the photoelectron increase. The frame B illustrates the values of the radial integrals for when with the change in the principal quantum number. The two figures for the atom hydrogen and rubidium, the results for photoionization was done with 36S state, while the radial integrals was done for the downward transition 36S to NB state. About the second remark, Thank you, Professor, for your notice formula. 1.5 contains a misprint. It should to be 0.5 instead of 0. About the third remark, Tom and Jerry naming is a metaphoric description to something summarizing the interaction. Tom and Jerry relation is well known to most of us, in which Jerry is provoking with his tricks Tom, whom becomes furious. The de-excited atom is like Jerry, releasing a photon as a trick to provoke the other atom like Tom, whom absorbs the photon and becomes excited. About the last remark, for hydrogen atom, there is enough complicated exact quantum mechanical formulas for radial integrals. When we comparing our semi-classical results with quantum mechanical results for Rydberg states, we put this fitting parameter and call it quantum factor to make a balance between results from our semi-classical formulas and the quantum mechanical results to become practically identical. Thank you.
Спасибо, Алла. Владимир Сергеевич.
Thank you, Alaa. Vladimir, are you satisfied with the answers? Yes, I am. Okay, our next member of the board, Maxim Golubkov, please, you have the floor. So what I want to say about this work, it impressed me. First of all, this work is quite relevant. So in this case, we're talking about the opportunity to control and manage this state. And in order to do this, we need to know the object quite well. And this work is dedicated to the fundamental study of the object, so that in the future we would have an opportunity to do something with it. Therefore, that's about the relevance, and I like the work a lot. Indeed, I'm going to read the remarks that I had in my review. First of all, in the dissertation, there is certain liberty in the designations which interferes with the correct perception of the text. For example, the Gaman value on page 39 indicates the overall panning ionization rate, and on page 50, the auto ionization width, so you should maintain the uniform designations. And second remark, in my opinion, this process 2.1 is not correct to call it an resonant Auger process. Certainly there is an analogy with the classical, but the classical Auger process involves the transitions with excitation of the inner shells of the atoms, and obviously this does not happen in this work. Third remark, it's not clear why the value of the polarization in table 1.1 page 16 is expressed as A and taken to the order of 2. If we correctly take into account the normalization of the wave function of the rydberg atom, the result should be A roughly n, and if we don't take it into account, that's A roughly n taken to the degree of 7. I've seen the answer in this in your report, so maybe that's a kind of misprint that the author has already corrected. And fourth remark, when specifying the 3% accuracy in the appendix A for calculating radial integrals in the framework of the semi-classical approximation for bound transitions, the author refers to the comparison of the values of integrals that are obtained using two types of semi-classical formulas. How is information about the accuracy of semi-classical description extracted from the data in tables A1 and A2? And in conclusion, I would like to say that all these remarks do not compromise the overall high appraisal of this work and the overall high value, and I believe that Abouzalam, Alaa, Mohamed, Ahmed deserves the academic degree of the candidate of sciences in physics and mathematics and specialization 139 plasma physics. Thank you so much. Maxim, Alaa, you can answer. You can answer the remarks.
Thank you, Professor, for your feedback and comments. About the first remark, in frozen gas, the Benign ionization rate and auto ionization widths are the same. But thank you for your advice. We should to use unique notation, and this will be taken into account in the next work. The second remark, we agree with this remark. Process 2.1 on page 36 is a pure Benign ionization process caused by long-range dipole-dipole interaction between atomic pairs. This resembles the Auger process, where an electron is also released as a result of the resonance transfer excitation in multi-electron. Therefore, the discussed process 2.1 is more correctly called the Auger-like process. Third remark, thank you, Professor. This is a typo. Fourth remark, thank you for this reasonable question, because we didn't illustrate how to find the accuracy from the tables. Table A1 and A3 provide a comparison between the two obtained formulas, A1 for short transition and A7 for long transition. The accuracy for short transition when delta n smaller than 10 established from the previous work from this work. So it was on the level 1%. For this reason, our semi-classical results for short transition have also the accuracy 1%. If we compare obtained results for short and long transition when delta n equal 4, the table shows that the accuracy of our results at the level of 3% here for this and this. Thank you.
Спасибо, Алла. Максим Геннадьевич.
Thank you, Alaa. Maxima, are you satisfied with the answer? Yes, I am. Okay, thank you. Now I would like to give the floor to Igor Ryabtsev. Yes, thank you. So the topic of the thesis is quite interesting. To my mind, the group that performed this work has been working with this topic for quite a long time. They considered the collision processes, or they worked with Rydberg atoms, and our group works with experiments with Rydberg atoms. And in the start of the century, we had joint work on collision ionization of atoms in beams, and now we switch to works with cold Rydberg atoms. And certainly the results of this work are of interest for experimenting scientists, and this is associated with the fact that all the applications that require Rydberg atoms require high accuracy of control of Rydberg atoms. For example, we need to perform quantum operations based on interaction of Rydberg atoms in conditions of high accuracy. Therefore, all the parasitic processes, including collision ionization and ionization of heat radiation, they should be taken into account and minimize. This work basically can help experimenting scientists in this regard, and it may allow choose optimal Rydberg states for quantum informatics, for example. And I liked the work as well. There are a lot of novel results that were published, and also the results were published in prestigious journals. As for the remarks, I have just two remarks. The second remark was already mentioned, that in this formula 1.5 you should replace 0 with 0.5, and that's with realization of first resonance. And as for the first remark, it was as follows. Basically, a lot of experimental works were performed in the study of spontaneous evolution of cold Rydberg gas, and experiments were performed by several groups. In the US group, Alan Singer in the US worked with that, Rolston in the US, and also they studied different processes that accompany the evolution of gas into plasma. And to my mind, in their works, these works were using rubidium, strontium, and so on. they made a conclusion that the basic mechanism of evolution are the charges that emerge during the ionization of rydberg atoms during heat radiation. And in this thesis, there was a comparison, and it was given that in certain conditions and high density, the speed of ionization can exceed the speed of thermal ionization. And it would be nice to see the comparison of theoretical calculations with experimental ones. However, the thesis did not do it. Maybe for the future you can consider this option. Maybe you will take some of the known experiments and conduct calculations according to the conditions, considering the theory that you developed. And it may be also of interest to calculate the dynamics of evolution of gas in ultra-cooled media. For example, if you calculate temporal dynamics, basically it's easier, simpler to compare experiments in this case. But overall, the thesis is really quite good. I believe it certainly deserves a very high mark, and the candidate for the degree, Alaa Abouzalam, deserves the academic degree of the candidate of sciences in physics and mathematics and specialization plasma physics. Thank you. Okay, thank you, Igor. Alaa, you can answer.
Thank you, Professor, for your feedback. About the first remark, of course, we took the first step. We took the first step towards building a self-constant model of the Rydberg gas time evolution by taking into account only the binary interactions. As a second step, it's important to consider collective interactions, which is quite painstaking work to describe the evolution of Rydberg gas at the diffusion stage. We must apply completely different technique based on kinetic equations of Fokker-Planck type with the inclusion of many relevant processes. It's important to note that the corresponding kinetic coefficients must contain our Benign ionization rate constants. But we will take your advice in our future work. Thank you. The second remark, this is a misprint, as I mentioned. So it will be 0.5 instead of 0. Thank you for your remark.
Спасибо.
Thank you. Igor, are you satisfied with the answer? Yes, I am. Okay, now I'd like to give the floor to Dr. Martins Ausench. Yes, unlike colleagues, I believe I was not as attentively monitoring the development of this topic at St. Petersburg State University. Therefore, I was pleased to see that the very good work for especially taking into account the fact that in experiment we have an opportunity to use highly excited Rydberg states, and it is also possible to study the interaction with smaller energy, with colder atoms. So certainly it allows us to find very interesting aspects to study. The second point that I liked in this work is that a lot of this work was carried out using analytical methods, and I believe that these are less analytical approximations that should be developed. When we develop them, well, we see that we use this technique less and less, and therefore we use certain prospect for the study of the topic, because numerical calculations are accurate and good, but sometimes they remind a kind of black box. You give something in the input, you get a result, and so on. Certainly we can study different dependencies, but I believe that's less obvious than when we use analytical methods. Therefore, it was quite nice to see the results that you obtained using analytical methods. And as for remarks, I had two remarks. One was a general one that does not require an answer, and as colleagues already mentioned, that's dealing with notations. Maybe you should have given a list of abbreviations in the start of the work. This would simplify the reading, but that's the remark that does not require any answer. And essentially, there are two questions that I wanted to mention. In the work, you pay attention to the radial part of interaction, and angular part of the problem is seen as something insignificant. And in real experiments, if Rydberg states are created by excitation, that frequently happens. As a rule, atoms will be polarized. And once again, from my point of view, quite frequently in similar problems, the radial part is resolved in a much more complicated manner, and angular part has certain generalized approach that is less dependent on the specific atoms that interact. And the more so, I believe that St. Petersburg can be seen as the places where quantum theory of angular moment is considered in the global scale, because it was developed by an outstanding expert. So the question is whether it's possible in the future to consider the interaction. Is it possible to include the angular part? And if it would be possible, I believe these results would be even more general. And the second question is dealing with the accuracy of analytical part. We understand, and at St. Petersburg State University, overall numerical methods of calculation of the full quantum calculation of radial dipole moments are quite well developed. And Alaa has already described it in her presentation, but I believe we can solicit more details if we compare the obtained results with full quantum mechanical calculation. Because as for the comparison with experiment, as far as I'm concerned, it's inaccessible right now. And this would allow us to make sure that the accuracy of these forms is quite good. But as the colleagues have already mentioned, I believe the quality of work is not questioned at all, as well as the quality of the results. And certainly I'm sure that Abouzalam fully deserves the academic degree of the candidate of sciences in physics and mathematics and specialization plasma physics. Thank you. Thank you. Alaa, you can answer.
Thank you, Professor, for your feedback and comments about the first remark. Yes, we have considered the most difficult part of the calculations, which is the radial part, because in our work we focus on the diffusion stage, where the appearance of asymmetrical pairs is accompanied by the uniform distribution of the excited states over Zeeman sublevels. It's possible to take into account the angular part, which is routine work and not effective in our calculations at the diffusion stage, but it will be considered in the future work. About the second part, at the same remark, experimentally it is not easy to measure Benign ionization, which considering the angular part, Benign ionization process becomes effective at the diffusion stage where the absence of the orientation, while the initial stage of preparing cold rydberg atoms, where the angular part can be considered, all atoms are excited to identical states at which Benign ionization process between symmetrical pairs is weak. Actually, at this stage, the photoionization process due to black body radiation is the dominant process. About the second remark, we have one electron atom, and for this quantum mechanical methods are very well developed to calculate radial integrals, but it's more complicated and rather time consuming compared to the semi-classical methods, especially in our work, because we have to calculate several million values of the radial integrals. For example, if we take a rydberg atom with principal quantum number 100, we have 100 partial transitions which contribute to Benign ionization. Each partial transition needs to calculate 4 outputs, up and down transitions. So to calculate the total Benign ionization rate for each quantum configuration of rydberg pairs, we have around 400 radial integrals output only for 1 point. So if we consider a 3-dimensional figure with 50 times 50, we will have 20,500 quantum configurations. We need about million values of radial integrals. In our case, yes, use of the classical quasi-classical approach is possible because we have derived acceptable accuracy of our results calculated around 15%, and this is a fairly acceptable accuracy of calculations. Thank you.
Спасибо. Доктор Марс.
Thank you. Doctor, are you satisfied with the answers? Yes, yes, I am. Thank you. Okay, and finally, my review. At once, I would like to say that I fully agree with the previous speakers. To my mind, the work is quite relevant and quite fascinating, both in the topic and in the, if we consider the results that the author obtained. My remark was on the opportunity to compare the results with experiments, but Dr. Martins has already mentioned that obviously currently it's not possible, and I would like to agree with him on the fact that applicability of analytical process in physical problems is quite an advantageous thing, because it allows you to analyze the result that you obtained and outline the path for further development. And in this regard, analytical approach, if it's possible, it is preferable. And finally, I would like to read this formal part because everyone missed it, therefore I'll need to read it. The thesis by Abouzalam, Alaa, Mohamed, Ahmed is a finished scientific study that complies with the requirements of St. Petersburg State University. And it complies with the requirements of the order. Article 11 of the above-mentioned order is not violated, and I believe that Abouzalam Alaa deserves the academic degree of candidate of sciences in physics and mathematics and specialization 139 plasma physics. Therefore, I believe there's no need to answer this question because basically you've already answered it. And that's basically it. I would like to thank all the members of the board, and I would like to ask anyone if anyone is willing to comment on the work. No one? Okay. Natalia, did we get any questions online? None? Okay. Okay then. Then, Nikolai, you have the floor. That's the thesis supervisor, Nikolai Bezuglov. Alaa, you know, Alaa joined the PhD course as my student 4 years ago. Before that, she was working with hot plasma with collision of heavy ions, and she had to shift from this hot climate to the cold one, and she started working with ultra-cold environments. Certainly, physics is just the same, but methods differ, because it's one thing when you have hot environment, and another case when you have cold environment, when there is no speed between the particles. And basically, there are a lot of applications of the results. You may get lost, and Professor Martes mentioned that basically this topic is has been developing for a very long period of time, and it's hard to find something interesting and novel here, and we managed to find it. Certainly, it was not. It was mentioned that Yefimov defended his thesis here as well, but he had the consideration of penning ionization and also other types of ionization. So penning ionization was not considered there fully, and he had just hydrogen atom. And in the experiment, those who are working with rydberg atoms and cold environments, in quantum optics, certainly these are alkaline atoms. You can cool them down up until low temperatures, and certainly we had to use the previous results. And once again, Yefimov calculated everything numerically, not analytically, and we worked with alkaline metal atoms. And during the PhD course, Alaa demonstrated very good results. She got all the A marks, if I'm not mistaken. She did everything on time. And yet another point, the chairman has mentioned that there are 3 publications. In fact, we submitted 4 publications, but one was not taken into account, because certainly when there is translation from Egyptian into English, there may be certain problems in spelling or certain inaccuracies, and one article was very poorly translated, therefore we need to take it out. But the most recent article, it was published after the documents were submitted, therefore she has 5 published works and 7 reports were delivered at conferences, so she has worked quite actively, and the results are quite good. And one of the reviewers mentioned a very good review. Indeed, it is. Therefore, I'm quite satisfied with her work and with the final result. Thank you so much, Nikolai. In fact, I had the same impression that Alaa had more works, but when I saw 3 works in the documents, I was quite surprised as well. And indeed, Alaa has more works, more published works. Dear colleagues, yet another point, formal point before we shift to the vote. Do we have any questions to the candidate for the degree, or maybe to Nikolai, or maybe to members of the board? Are there any questions to anyone? No? Okay. The question to the members of the board, then, and to the candidate for the degree. Are there any remarks or questions connected with the procedure of our defense? Maybe the questions associated with the remote mode access. And according to the procedure, I need to ask you all. Not necessarily. Okay. Okay. Okay, you can nod if you have some questions. Okay, no questions. Okay. Now we shift to the most important part of our session, to the vote on the thesis. And judging by the speeches of the board members, the opinion is quite uniform, and there's no need to hold a closed discussion to negotiate. Do you agree with me? No need for that. Okay. Okay, thank you, colleagues. Now let's shift to the vote. And I raise the question. We're going to have an open balloting. I'll ask everyone, and everyone will have to say what he or she thinks about it. So, let me raise a question on the award of the academic degree to Abouzalam, Alaa, Mohamed, Ahmed. and the scientific specialization is 139, plasma physics. So let me remind you that the decision of the Dissertation Board on conferring the academic degree is positive, provided more than 50% of the board members, but not fewer than 3 people, voted in favor, in conformity with Section 23 of the Order on the Procedure of Granting Academic Degrees at St. Petersburg State University. Okay, Professor Smirnov, what's your opinion? I believe Alaa deserves the award of the academic degree. Professor Sakhamelinov? Yes, I also believe that she deserves the academic degree. Professor Golokov? Yes, I agree with a colleague. Alaa deserves the academic degree. Professor Reptsov? Yes, she deserves the degree. Professor Martzes? Yes, certainly, she deserves the academic degree. And my opinion is just the same. I believe Alaa deserves the academic degree of the candidate of sciences. So, distinguished colleagues, dear guests, I would like to announce that out of the 6 members of the board that took part in the vote, 6 voted for the award of the academic degree to Alaa, and therefore we award the academic degree of candidate of sciences in physics and mathematics and specialization 139, plasma physics, to Alaa Abouzalam. Distinguished colleagues, due to the fact that our session is held online, I would like to ask if the members of the board, I beg your pardon for these repetitions, but the procedure is as follows. Therefore, I need to repeat that. I would like to ask if the members of the board or the candidate have any questions or comments on the procedure. None. No questions. Okay. Then we give the floor to Alaa for conclusion.
I'd like to express my gratitude to highly respected chairman and members of Dissertation Council. Thank you, the referees, for times and the efforts during the academic year vacation to conduct this final stage of my PhD degree. Thank you for your valuable discussions and questions. Those enriched my understanding of my work and generated potential points of research to consider in my future work. Special appreciation to my supervision, Professor Bziklov Nikolai Nikolaevich. Thank you, sir, for your supervision and guidance through the whole work to come to this successful end to get my degree. It's added to my career in research as remarkable knowledge and experience to tackle in my future personal and professional lives. Professor Timofeev Nikolai Alexandrovich, the head of my department in St. Petersburg State University, thank you, sir, for your help and support along this work. Many thanks to the employees of the department for ensuring the activities of Dissertation Council, for the excellent work of processing documents for defense, and in general for organizing today's meeting. I am also in debt gratitude to my colleagues who were supportive through my time here. Karbova Natalia Vladimirovna, thank you for your enthusiasm and professionalism. My biggest thanks to my parents and sister for all support you have shown me through this research. A special appreciation to my husband and son. Your understanding and support through these 5 years were the core to my success. It was not easy to do that it without you. You are my reality, my origin and destination. Wish all good day. Thank you. Thank you.
Alaa, we congratulate you with the successful defense. We wish you further success, and we wish you to preserve these connections with our university, with a group of Nikolai Bezuglov, and certainly we wish you further success in your work. Thank you. So let's give a hand to Alaa. So, distinguished members of the board, I would like to thank everyone for taking part in our session. I would like to thank those who are not from St. Petersburg, those who participated remotely, and I would like, I'll be happy to see further joint projects. We're going to have more defense sessions later on, so please, I would like to wish you good health and further cooperation. Thank you, everyone. Yes, thank you. Yes, I therefore close our session. Thank you, everyone.